Hi there. Sorry, Nola is sick, so I'm staying home with her today. So here's the lesson for 2.1. Should go pretty quickly. Yesterday, the students in second hour had a lot of time to do the homework, and most of them were done before they left class. So make sure you have one of the note sheets. You don't need a calculator today for anything. And just follow along and get your homework done, and I should see you guys on Friday. So today's lesson, as we start off chapter 2, is about parent functions. We're going to start off talking about increasing, decreasing, and then something later called continuity. The continuity and the increasing, decreasing thing all deal with domain, and so using the parentheses and the brackets and infinities and whatnot. So if you've struggled at all with domain and range, then this could be an area where you continue to struggle, or it could be an area where you start to gain some ground on that topic and try to finally start to figure out what's going on with those things. So hopefully take it on that positive note that this could be a chance for you to kind of start figuring out what's going on with domain and range and stuff like that. So what we're looking at here first is the idea of a function increasing, a function decreasing, or a function being constant over specific intervals of the domain. Okay, so we're looking at places where the between these two x values where the function would be increasing. And so what we want to pay attention to is that happens as the graph rises from left to right. So it's that left to right part here that's important. That when we read domain, it's always from that left side to the right side. What you don't want to do is get lost in like arrows, because this function could have an arrow going up and an arrow going down. This function could have an arrow going up and an arrow going down. And so if you just look at arrows, like, okay, this one's got an arrow pointing up, it must be increasing. And well, this one also has an arrow pointing up, so it must be increasing too. It's not how that works, so you're really careful about that. What you want to focus on is as you move from the left to the right, what's the function doing? So I'd really suggest that you put your pencil on the graph and say, as you move it from left to right, you're forced to rise also. Or as I move from left to right, I'm forced to fall along the graph. Or as I move from left to right, I'm not moving up or down, so it's constant. So always in that direction, from left to right. So putting your finger on there, putting your pencil on there, and tracing it, saying, as I'm going left to right, I have to go up. Or as I go from left to right, I have to go down to stay on the graph. And so just getting your brain connected to the graph a little bit more of that physicalness it can be really helpful. So I would really suggest you do that. So as we move left to right, the graph is going up. It's an increasing interval. As we go left to right, the graph is going down as a decreasing interval. As we go left to right, the graph remains flat, horizontal. That is a constant interval. So we got a couple examples here. And this graph here is upside down, probably would have arrows on the end, and this curve here would have arrows on its end. And so these two problems are very similar to some of the problems that you guys have in your homework, whereas they give you a picture, or they'll want you to come up with a picture and then look at it over just a particular interval. And so here they're saying over the interval from negative infinity to 0. So what they want to do is they want you to start on that left end. And again, it's negative infinity because it's left, not negative infinity because it's down. So the left end and all the way up to 0. So as we start on that left end and head towards 0, we are increasing. We're moving up with every point. So that function is increasing over that interval. So you got to be careful because it looks like that arrow is pointing down, and it's actually increasing at that spot, that interval. Okay. And then the next interval is saying, well, now start at 0 and head towards infinity. Remember, that doesn't mean up, that means to the right. So start at 0 and head right. What happens? So as I start at 0 and I try to head right, I am forced to fall with the graph. So that graph is decreasing over that interval. Okay. So again, just don't get caught up with the arrows, looking both arrows go down. Ooh, they must be decreasing everywhere. Nope. The left side is increasing. It stops increasing here, and then it starts decreasing to there. Okay. Similar question here says, different graph. It says so reading that negative infinity is from the left to 0. So on the left end, as I try to move right and head towards 0, I'm moving up each time. So that function is increasing over that interval. And then as we go back to 0 and say, okay, as I head to the right, not head up, as I head to the right, I'm forced to also go up. So that is also increasing. So again, just notice how the arrows can lie to you. Okay, so don't listen to the arrows. Okay, so this half of the graph is increasing, and this half is also increasing. So we'd say as this whole graph is increasing, this whole function is increasing, or the function increases across its entire domain. Is another way to say that. We'll talk about that later. Too, that this first graph was increasing and decreasing. There was no part that was constant. So if it was asked where is it constant, you could just say never or none or NA, something like that. Just this graph had just increasing. So if asked said, hey, where is it decreasing, you just say it's not decreasing, or it's never decreasing, or none, or something like that. So it certainly doesn't have to be all three. And then again, just turning over our definitions of what increasing and decreasing and constant are. All right, so there is just these two graphs down here. All right, from the left end to this point, it's increasing. From the right end to this point, it's decreasing. From the left end all the way through, it's increasing the whole time. Another example here. This will definitely be how some of the questions you'll be asked to do will be worded. It's going to ask you, determine intervals where the function's increasing, decreasing, constant, and what's the domain and the range. What I like to think about with these problems is you don't have to answer the questions in the order that they're given. I like to just read the graph and see where I see increasing or decreasing or constant first, and then just write that part down. So I'll start with A, B, and C, just kind of looking at the graph. And again, we're talking about intervals of the domain, so I want to think about that left side and then move towards the right. So as I go to the very left end of the graph, I see that as I try to move right along the graph, I'm being forced to move down. So what's actually happening here is that this graph is decreasing along this part. And though it started decreasing at -8, that's a hard -8 since it's a closed dot, and it stopped decreasing at -3. Again, it's not the y values I care about; it's the x values, because it's domain we're talking about. So the -8, and it stopped decreasing at -3, and again it's hitting -3, so it gets a bracket on both of those. So this is the interval where it's decreasing. And then what's happening after -3? So from -3, as I try to move right, I'm being forced to also move up. So it's increasing along this interval. And so where is it moving up from? From -3 to 1. So, and again, it's starting at -3, so it's bracket. It's finishing at 1, so it's hitting 1, so it's a bracket there also. So there's the interval where it's decreasing. And what's happening after 1? So it's constant from there on out. So at 1, it starts being constant, and then it goes forever to the right. So it's starting at 1 and then continues on for infinity. Now this graph does all three things. It does have a constant part and an increasing part and a decreasing part. It certainly doesn't have to, just like we saw on the last things. There certainly could just be 1, it could be 2, it could be all three. So it can be a mixture of things, so don't get caught up in thinking that it has to do everything. Then what's the domain of this graph, or this function? So again, leftist to rightist. It's really a phrase you want to make sure you know. Leftist, rightist. So the leftist point is -8, hard -8, and then it goes right forever. So bracket -8 to infinity, parenthesis. And then what's the range? So leftist, rightist, and then lowest, highest. So the lowest y value is -1. The highest y value is +4. So from -1, it's hitting -1, so that's a bracket. And it's hitting 4, so that's also a bracket. So there's our domain and our range. Okay. From there, we move to what they look like. Here's your increasing, decreasing. Okay. Again, I would just suggest you start on the left side, see what it's doing until a certain point. All right, it's decreasing to here. Oh, now it's increasing from here to here. No, okay, now it's constant from here to here. Just write those in the order that you see them. So we saw that first, then we saw this, then we saw that. I think that's easier to do. Home parent functions, and so with these are things you're going to want to memorize at some point, like their shapes, as we move towards, if I just draw you a function and say, hey, can you write the equation of this? You need to know what the function, the shape of it is telling you about which function it is, whether it's x or x squared, shape looks like, so you can say, well, it's this function. Or when we go into piecewise functions, that you understand, again, those shapes, they show you which function is being used. So you will need to know basically a sketch of the parent functions. So just something visually I want you guys to start memorizing. Okay, so there's 5 of them, and again, it's just a quick sketch. It doesn't need to be perfect, just a real general idea. And I should be able to ask you, say, hey, what does x squared look like? And you should already know that. You have a lot of experience with x squared functions, but then it gets really where you need to be focusing. So the identity function, that's f of x equals x, or y equals x is another way to think about it, right? And and x is just a linear function, so this is just a line. And y equals x is the same thing as saying, like, well, if x is 1, then y is also 1. If x is 2, y is also 2. If x is 6, then y is also 6. Or if x is -5, then y is also -5. So it's the line that goes from the top right corner to the bottom left corner. So this is the most basic line there is. And that would have arrows on both ends. Right, so like 1, 1, 2, 2, 5, 5, -10, -10. Like, that's why it's called the identity function, because the x's and the y's are the same thing. They're identical. So identity function, y equals x, f of x equals x. It's a line, straight line, top right to bottom left. It's the most basic line there is. So domain range, leftist to rightist, so left end, arrow pointing to left forever, right end, arrow pointing to right forever. So that's our negative infinity to positive infinity, all real numbers. Oh, Lord. Okay. And we look at that lowest to highest. So the lowest point is negative infinity as it goes down forever. Highest point goes up forever. So also all real numbers. Pretty easy. Squaring function. So x squared, right? You should already know what this is going to look like. It's going to be a parabola. We just think about throwing some numbers out if you need to. If you say, okay, what's 0 squared? Well, that's 0. What's 1 squared? That's 1. What's 2 squared? That's 4. What's 3 squared? That's 9. We can't plot anything higher than that. So 0, 0, 1, 1, 2, 4, 3, 9. Remember, parabolas are symmetrical, so we get the 1, -1, or -1, 1, -2, 4, -3, 9. So here's a parabola. You notice that its vertex is at 0, 0. That's why it's a parent function. It starts at 0, 0. Just like our line went through 0, 0 over here. So there's our parabola. So what's x squared look like? It looks like a parabola. Domain, so leftist to rightist. So the left end is an arrow. Again, don't pay attention that it's pointing up because we're worried about it moving left and right. So it is moving left forever, very slowly. And then as we look at the right end, it's also moving right very slowly forever. So we get negative infinity to positive infinity. And lowest to highest, so what's the lowest value? 0, it's hitting 0, and then it goes up forever. So hard 0 bracket, and then up forever. So there's your squaring function again, something you should be very familiar with. Squared really is just this half of the parabola, but just turned on its side. So that's why I say the half curve, or half parabola, to its full. Then try to memorize the domains and ranges also. So if you can quickly sketch it out, and again, it doesn't need to be memorized those, or x cubed or square root of x, like you need to know x cubed and square root of x. Cubing, so what happens when we cube some numbers? So like 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. That's as high as I'm going to be able to go. 2 cubed is 8, and then -1 squared is -1, or cubed, sorry, and then -2 cubed is -8. So we get this here. So what does the cubing function look like? Right? It's how you're going to memorize it. I like to think of it as a a vertical S, stretched out vertical S. Oh, sorry, I'll try that again. Okay, that's how I remember it, stretched out vertical S. Domain, so what's our rightest point? So, or sorry, leftist point, so that arrow that's going to slowly move left forever. Rightist, that arrow that's going to slowly move to the right forever. So infinities. And then lowest to highest, our lowest, arrow pointing down forever, arrow pointing up forever. So our infinities again. So all real numbers. Then it's going to square root. So think about what types of numbers we can't square root. Right? We can't square root negatives. So the lowest number we can square root is 0, and the square root of 0 is 0. Think about other numbers that are easily square rootable, like 1. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Right? And then those are the highest ones we can fit on here. So plotting those. So 0, 0, 1, 1, 4, 2, 9, 3. All right, so what's this graph look like? So as we make that curve starting at 0, not an arrow there, and heading off to the right. So when I talk to myself about what does the square root look like, I say it's the half curve to the right. And when I say half curve, or I might say half parabola, because if we look at x to the right. So again, no arrow here. It's a hard stopping point. And then an arrow on the right end. Think about the domain. So our leftist point is at 0, and then it goes to the right forever. So hard 0 to the right forever. What's our range? Lowest point, 0 again, and then goes up forever. Again, albeit very slowly, but it does go up forever. So again, hard 0, and then up forever. So there's our square root function, so that half curve to the right. So we've got this vertical S here with our x cubed, and we've got our half curve to the right for our square root of x. All right, and last parent function, cube, right? So 8 has a cube root, and it's 2. You'll be able to do the domain and range from the picture. That's going to be much more awesome if I say, look back at one of these, right? This graph is also continuous over its whole domain. Even though there's nothing here during this function's domain, there's no breaks or holes. I don't have to pick up my pencil. Parent functions, again, you guys should have x and then cube root of x. Those are the ones memorized. So the last shape that you need to start trying to memorize. So cube rooting. So what types of numbers can we cube root? So the cube root of 0 is 0. What number times itself 3 times is 0? What number times itself 3 times is 1? Well, that'd just be 1. What number is easily cube rootable? If we go back to, so 8 is cube rootable easily. So the cube root of 8 is 2. And in the same way, we can, we can't square root negatives, but we can cube root negatives, because the cube root of -1 is -1. -1 times -1 times -1 is -1, so that means it has a cube root. And in the same way, -8 has a cube root and it's -2. So 0, 0, 1, 1, 8, 2, and then -1, 1, and -8, 2, -2. So this graph is, if you recognize, it's just another S, but it's a sideways S instead of a vertical S, stretched out. So this is just a stretched out S. Again, that's how I remember it when I'm trying to memorize the shapes. So again, you will need to know those shapes. I think you will really struggle with some other things that we do if you don't. So I would start memorizing that, and that could be something as simple as looking at your notes, covering up the picture and saying, what does the x cube look like, and then looking at, make sure you know it. But you need to do that over and over and over again to memorize it. So just like when you're studying vocab words or something, you need to practice covering them up and try to memorize the definitions, or make 5 flashcards real quick. What's the cubing function look like? What's the identity function look like? Okay. Domain, left end arrow, right end arrow. So we get all real numbers. There's a low arrow and a high arrow, so all real numbers. Okay. So the domain and the ranges aren't things I think you guys need to memorize. If you can draw the picture, then, hey, what does x cubed look like? And so you just say x cubed, that's my vertical s, like that. It's a quick sketch. Okay, what's the square root of x look like? So, ooh, that's my half curve to the right. So start at 0, that, right? So something really simple. That was pretty bad, but so just like that, just a quick sketch. That's all you need to be able to do, but just to memorize that. Okay. Oh, what's x squared look like? Boom, boom. Parabola starts at 0, right? Vertex is at 0. So again, that idea that that 0, 0 is important. So hold on to that. Okay. All right. So there's your parent functions. Again, 100th time here, you need to memorize what those look like. Like this graph right here, and say if I try to draw this with my pencil, so it's like I can draw the whole thing without picking up my pencil. So that's a continuous graph over its whole domain. So is there's a bit of time questions. All right, this last idea of continuity, you get really careful because we talked about constant, which means flat, and this is continuity or continuous, which does not mean flat. It also does not mean goes on forever, so that's something you got to get out of your head. It's a really common misconception about continuity is that it goes on forever. What that means, right? So a function is continuous over an interval. So there's that again. If it's hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. So we look back real quick. Graphs are both continuous. As I try to draw this graph, so this is a rational function. You guys have done those before. It has an asymptote there, has a break. So as I draw this part of the asymptote, and I pick up my pencil, and then I have to, or this part of the graph, and then I pick up my pencil, and then I can draw the other part of the graph. So I had to pick up my pencil, so that means there's a discontinuity here. Something is breaking it. Okay. Same thing here. This is a piecewise function. So as I draw this part, got it. Oh, then I have to pick up my pencil. Now I can draw this part. So this has a break in it or a hole. So these graphs are both discontinuous at x equals 1. Okay. There's something going on there that's breaking it. Most of the time I will not ask you guys if it's a black or white. Is this graph continuous or is it discontinuous? So it's going to be where is it continuous? Okay. So this graph is continuous all the way from the left if we assume there's an arrow here until we get to 1, and then it's not continuous anymore. So the interval of negative infinity all the way to 1, and it's not quite reaching 1, so it's a parenthesis, it would be continuous. And then also on the other side of 1, it starts being continuous again. So as we come from the right, it's continuous, continuous, continuous all the way to infinity again. So that would look like this. And then it's continuous at 1 again, but just on the other side of 1, so like 1.0001, and then forever. So that would be the intervals where this graph is continuous. In this particular one here, as we approach, and again, if I think that's an arrow, as I approach from the left, it's fine until I get close to 1, and it stops just short of 1. That's what that open circle means. It doesn't quite reach 1. So it'd be from negative infinity to 1 with a parenthesis, and then also, and then as we look at the next part, so here's a closed circle. That means so starting at 1, so at 1, and then to the right forever. Again, the thing with arrow, not that it's going up, but that it's going right forever. So let's get a bracket 1 to infinity. So that's where it's continuous. Those are the intervals where it is continuous. Okay, and that's what you guys would mainly be asked to do, not just is it continuous or not. So you say where is it continuous. Those of you that have done this, like the intersection or union notation, we aren't going to be doing that in this class. We'll just say, just use an and symbol, that's fine for what we're going to do this class. So, all right, so here's a couple examples of that. Remember, they just are worded to kind of determine the intervals, again, of the domain where the function is continuous. Again, only domain, so just think about x values, not y values. Okay. So I'll just say we got some arrows here. Arrows all over this. Okay. So where are these functions continuous? So again, I want to start on the left since we're talking about domain. So I got an arrow going to the left. As I head towards 3, it starts to turn away because of that asymptote. So it's never going to reach 3. So that means this graph is continuous from negative infinity to not quite 3, so like 2.9999, so it's parenthesis. Oh, but then on the other side of 3, so 3.0001, it starts again, and then it's continuous and keeps going, right? So there's no more breaks in there. So from 3, so and from 3, again, parentheses, because we're just on the other side of 3, to forever to the right. So that's where that graph is continuous during those two intervals. And then look at the next example. So here, look at that left side, trace along. Do I have to pick my pencil? Nope, 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 nope. All right, so nowhere along there did I have to pick my pencil. So that means that this function is continuous everywhere. There are no breaks, no holes. So this is over all real numbers. Okay, so no breaks, no holes would be all real numbers where it's continuous. And the last one, so we start on the left end. Do I have to pick up my pencil? Do I have to pick, nope, 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 follow along. Everything's good. Oh, something's happening right there at 2. That's a hole. And something most of you probably haven't seen before. It's something we will talk about later with rational functions, what's happening here. But this is what a hole looks like. It's just a little open circle on the graph. So coming from negative infinity, everything's good until we hit 2. It's like I plug in 1.999, I get an answer. Then I plug in 2, no answer. And then we go on the other side of 2, 2.00001, and get an answer again. And it keeps on going to the right forever. So what's going on with this graph? So from negative infinity, so from the left side all the way to 2, but not quite 2. So parenthesis, and then and on the other side of 2, and then to the right forever. It's continuous. So again, be careful not to get stuck with y values. This continuity stuff is a little bit easier than the increasing, decreasing, not to do that. So you don't get tricked by the arrows as much. Okay, but so just that idea if you have to pick up your pencil or not. So okay, so that's continuity. We saw here, strangely, and the pages are online. Ooh, I needed to show you something. I don't know if I can do that here. So 23, I'll talk about it real quick. It asks you to when you look at the instructions, it says graph, whatever function on a calculator. So you might need a calculator from the sub. Or you can always use an app on your phone or on your, use Desmos on your computer. It says graph like x to the 5th, and I look at it over a certain domain and say if it's increasing or decreasing. Number 27 says use f of x equals the negative absolute value of x. So if I graphed that on my calculator and they say use the standard window, so that's hit that zoom 6 button, so you get that nice little 10 by 10 window. Okay. If I graphed that function, it would look like this. It'd be an upside down V. And then it says, what's it doing from the interval negative infinity to 0? It says, look at it from this, right? And so what it's asking for me to do, and then it says, is it increasing, decreasing, or constant? So your whole answer is just one word. So as you look at it from the negative infinity, which means that left side, so go to the left end of the graph, and all the way to 0, what's happening? So from the left end to 0, it's increasing. So as I try to move right, I'm forced to move up. So that means that my whole answer here for this part of the problem is that the graph is increasing. And then one of the other problems might say, well, what's it doing from 0 to negative or to positive infinity? And so I'd say, okay, well, it's just one word answer. So from 0 to, as I try to move to the right, I'm forced to move down. So saying, okay, well, it's decreasing in that part of the domain. So it's going to be kind of like we did the very first problem. You to graph it on the calculator, because you may not know what this function looks like. It's not something I'm asking you guys to memorize. So it's just say, hey, graph this on the calculator so you can see what it looks like, and then you can look at the picture and talk about its domain, or the intervals of its domain, like what it's doing, increasing or decreasing or constant. So that's what 23 through 26 are all about. But it seems like a long assignment, but really not any math you're doing. You're just going to write down a bunch of intervals and a couple of words. So shouldn't take very long. Really should be able to get it done while you're in class. Remember, there's books in the book cabinet if you need to borrow one, or the pages are online. So on the class page. So all right, good luck, and I'll see you guys Friday.